So thanks for coming, despite the very bad weather. Oh.
It's coming in through.
Oh, okay. So let me recall the problem I was studying. Okay. So I'm on a four-dimensional manifold, M with a metric G. And I was studying the problem of finding a conformal matrix to the given one with the constant Q-curvature. Okay, so we saw how Q-curvature transform under a conformal change of metric. And so the problem of finding a matrix with the constant Q amounts to solve that problem P. Okay, so in that formula, PG is the dependence operator, which is displayed there. So the main part is the Laplacian squared. And that's a variational problem. So the Euler-Lagrange functional associated to that equation is the following one, denoted by 2. Okay, so QP in this formula is the integral of the Q-curvature, which is a conformal invariant. So that we saw last time. And we saw that this functional is defined on H22 of M. Okay, functions with the first and second derivatives in L2. Okay, so the results I was describing are a theorem by Cheng and Yang in 1995. So they assume that the dependence operator is positive definite, that the total Q-curvature is less than 8 pi squared. So this is the total Q-curvature of the sphere. And then they prove existence of solutions. And they prove it using the coercivity of the function. So we have the Adams inequality. Okay, so forget about this part for the moment. So if the dependence operator is positive definite, then you can control the logarithmic term in terms of 1 over 8 pi squared times u pju, the quadratic part of the function. So if the dependence operator is positive definite, and if qp is less than 8 pi squared, then the function becomes coercive, and you can find solutions as global minima. Okay, this is what we saw last time. And I started explaining this other result, so joint work with Jadli. So we relax these assumptions. Okay, we assume that the dependence operator is invertible. Okay, it just has trivial kernel, and that QP is not an integer, positive integer multiple of 8 pi squared. Okay, then we can still solve the equation. So I showed last time that if one of these two assumptions fail, then the Euler-Lagrange functional is not coercive anymore. Okay, so you can find functions with a large H2 norm for which the functional becomes very negative, actually arbitrarily negative. Okay, so you cannot minimize anymore, and you want to find saddle points. Okay, so I defined this very abstract scheme which allows to find critical points. And let me recall it. So I'm considering a C2 function defined on the Hilbert space, which satisfies the Pallet-Smale condition. Okay, so if you have a sequence for which the function converges and for which the gradient of the function along that sequence goes to 0, then it has a converging subsequence. Okay, so that's the Pallet-Smale condition. And then you start with some set A. So an easy example would be, say, an n-dimensional ball. Okay, compact topological space, subset B of A. So that could be, for example, the boundary of this ball S n-1, and the continuous map from the ball into the Hilbert space. So we saw this example, okay, in R3, okay, a sort of model. So f of xyz would be z squared minus x squared minus y squared. Okay, so this function is bounded from below on the z-axis. Okay, but if you move in the xy plane, then this becomes very negative, just like the Euler functional for the dependence equation. Okay, so in this example, B would be a circle S1. Okay, in the xy plane. So this function assumes the value -1. So the idea is that if you move far in the xy plane, then this function becomes very negative. Okay, but it's bounded away from 0, so it's non-negative when you stay on the z-axis. Okay, so we first consider some sort of embedding. Okay, from of this set B into the Hilbert space. Okay, where tentatively the function f is small. Okay. And then we extend this continuous map to the set A. And we consider the class of functions which are extensions in A of this map HB. Okay? So this would be a sort of covering of, say, you can imagine this to be a sort of graph on the unit ball. Okay? In this example, we took B to be S1 and A to be the unit disk in R2. Okay? So in this example, you consider continuous maps from the disk into R3, okay, which extend the identity on S1. So there are two assumptions on F. The first is the Pallet-Smale condition, okay, and the second is a sort of gap condition. Okay, so you require that there is some sort of gap between the supremum of the map on the set B and on the image of the set B, okay, under the map HB, and the supremum of any extension inside A. Okay, so this condition which I call delta. So if you have the Pallet-Smale condition and that condition, then you define this number, okay. So you take all the suprema of the extensions and then you take the inf, okay. Then this is a critical value of the functional. So how did we prove it? We prove it using a sort of gradient flow, okay. So take any extension h in that class, okay, and you can let it flow by the gradient flow of the functional, okay. You can use some cutoff, thanks to that condition star, which keeps the map invariant. So still, not invariant, but still in that class, okay. So the boundary is fixed, and then you are somehow flowing the top value of this map, okay. The condition star allows you to use that cutoff. So this flow produces some Pallet-Smale sequence at level CAB, and then by this Pallet-Smale condition you get a critical point of F at that level. All right, so in this example we have this gap condition. Why? Because on the circle, the map F, the value of F is -1, okay? But each time you cross the z-axis, then F is greater or equal than 0. Okay, so the condition holds with delta equal to, say, 1/2. Okay. So some remarks. First of all, is that the Pallet-Smale condition can be substituted with the deformation lemma, okay, because we use the deformation lemma to prove that result. So the deformation lemma tells you that you have two possibilities. Either you have no critical points within some strip, or either you have a critical point within some strip, or you have no critical points, and then you can deform one sublevel into the other. Okay, so this is what we're doing with this gradient flow. The second is that this condition star automatically produces Pallet-Smale sequences, okay, because this is a sort of bound from below on the supremum of F. So if you don't have a Pallet-Smale sequence, okay, it means that when you use a gradient flow, you keep going down, okay? And in this case, you would go below this level CAB if you have no Pallet-Smale condition. So the gradient flow would push you down too much, in a sense. So it means, this condition star means that if you run a gradient flow on such a map with a cutoff, then you get stuck at some point, okay? And something which I should say the other time is that usually when you choose such sets A and B, A would not retract onto B, okay? Because otherwise you could choose a map here which somehow shrinks to HB, okay? So in that case, the method won't work, okay? So say this is not required in the assumptions, but it's a usual assumption that you make. And we saw this example with this simple function, okay? So the last time I was treating the easy case in which QP is still less than 8 pi squared, but when lambda1 of the Penitz operator is negative, okay? So this case does not fit into the assumptions of theorem 1. Okay, so what did I do? I was somehow inspired by this easy example. So you denote by W minus the span of the negative eigenspaces of PG. Okay, so you will have, say, k bar negative eigenvalues. With eigenfunctions phi 1, phi k bar. Okay, and W plus would be the complement of W minus. Okay. So what was the choice of A and B in this case? Okay, so B would be the unit sphere in R k bar minus 1. Okay, so somehow you count the negative directions of the quadratic part of the functional. In this case, it's 2. Okay, so those are the ones that would give you trouble with the coercivity. Okay, when the functional goes down. Okay. So you have this case when the dependence operator has negative eigenvalues. So we evaluated the functional on straight lines in the negative eigenspaces. Okay? So the quadratic part of the functional, UPGU, somehow pushes you down. The other two parts are kind of linear. Okay? So one is really linear, the other is asymptotically linear. Okay? So the function is going down exactly as in this case. Okay? So here I'm choosing the dimension of the negative eigenspaces minus 1. Okay, so B would be this set, and A would just be the unit ball in k bar dimensions. Okay, so what is HB? I want to consider a large sphere into the negative eigenspaces. Okay, so for R positive, I define HB on so elements in this sphere can be denoted by say in this sphere are denoted by, so sk bar minus 1 is the set of elements x1 xk bar in R k bar with unit norm equal to 1. Okay, so HB of x1 xk bar can be chosen to be R times the sum of xi phi I for I running from 1 to k bar. Okay, I'm embedding a large sphere into a negative eigenspace of the quadratic part of the function. So you can imagine enlarging this circle. Okay, the asymptotics of the function is somehow the same as this one, very naively. Okay. All right, so we chose A and B. Okay. I will prove the Paley-Smale condition. What about this gap condition star? Okay. I recall that we had somehow cheap improvement of the Adams inequality. Okay. So even if the dependence operator is not positive definite anymore, but if you have a bound on the negative component on U, okay, so the component in W minus, then you still have the Adams inequality. So what does it mean? So you can picture this axis. So this would be the counterpart of, say, W minus, okay, negative directions. And this would be somehow W plus, okay? So when you stay in a neighborhood of the W plus axis, the functional is still bounded from below, okay? So what's happening? On this big sphere, the function is going to minus infinity. If you stay on the axis, then you are bounded from below. This means that we do have this condition star if you choose R sufficiently large. Okay? So we have indeed some difference. So how do you prove that this condition star is reached? You can use degree theory. Okay? So you look at the projection onto W minus of any extension H of this map. Okay? There will be a point in between where this map is 0. Okay, so where the projection is 0, which means that you are on the W plus axis. Okay, so we have this condition star. Let me prove the Paley-Smale condition. In fact, I won't really prove the Paley-Smale condition. I will prove that, so I remarked that condition star which we have gives you Pallas-Mail conditions, okay, I will prove that Pallas-Mail conditions are bounded, okay, and then I will consider the weak limit of such a Pallas-Mail condition. So that will be a solution of our equation. Yes?
Star gives you a Pallas-Mail sequence, but you don't have Pallas-Mail condition.
No. In fact, so this gives me a Pallas-Mail sequence. I'm going to show that Pallas-Mail sequences in this case are bounded, okay? And then I want to prove that the weak limit is a solution. So this is somehow the standard result in min-max theory, so the one you find on books. And I'm making these two remarks because I need to use both. Okay, so yes?
So in the proposition 1, actually we can assume that there's no Pallas-Mail condition, right?
Yeah, you can substitute the Pallas-Mail condition with the deformation lemma. Yeah, you need that. So yeah, these are some kind of refinements which I'm going to use. So if you read a book on these things, then that's what you will find in general. Okay, so the claim is that Pallas-Mail sequences in this case are bounded. Okay. All right, so by condition star, we get that there exists a Pallas-Mail sequence UN. Okay, so what does it mean? It means that 2 of UN is tending to some constant C in R, okay? And that the derivative of the functional at UN is tending to 0. Okay, so let's apply the derivative of UN. So the gradient is now tested on UN minus, so the component into the negative eigenspaces. Okay, so what is this? This is 2 times the integral of UN PG of UN minus. Okay, this is a quadratic form, plus 4 integral of QG UN minus, and minus 4 QP log of, integral of e to the 4 UN minus divided by the integral of e to the 4 UN. Okay, so I just differentiated the Euler functional, and the variation is UN minus, the negative component of UN, according to that splitting. Okay? All right, so notice that the eigenfunctions satisfy a nice PDE. Okay, so every phi I belongs indeed to L infinity of M. So what do we have here? Okay, so this term is equal to 2 times UN minus PG of UN minus. Okay, so this is a big O of norm of UN minus in H2. When I use the norm here, I mean H2 norm. Okay, and this quantity, so it's a weighted integral of UN minus. Okay, but somehow I'm normalizing the measure. Okay, so this quantity is bounded by the norm of UN minus in L infinity. Okay, but on this finite dimensional space, the L infinity norm is equivalent to the H2 norm. Okay, and this quantity is a quadratic form which is negative definite on UN minus. Okay, so this quantity is bounded from above by minus some constant C, which will be actually lambda 1, times the norm of UN minus squared. Okay, and the rest is a big O of the norm of UN minus. Okay, so what does the Pallas-Mail condition mean? So that this is going to 0. Okay, so when I test on UN minus, I find that this is a little O of the norm of UN minus when n goes to infinity. Okay, so this implies immediately that the norm of un minus is uniformly bounded. Okay? All right. So now, maybe I can erase. No, nothing here. Okay, so the norm of un minus is uniformly bounded. Okay, I use the fact that the functional is converging to some real constant. Okay, so somehow un minus is not bothering us anymore because it's uniformly bounded in H2, but also in L infinity. Okay, so the fact that now the function is converging and the Adams inequality implies also that in fact un is bounded. Okay. Also, say the positive part of un is bounded, okay, which implies that the norm of un is bounded. Okay. So this implies that un converges weakly to some function u naught. Okay. And the claim is that u naught solves your equation. Any questions so far? No questions? Okay, everything is fine. Yes. Are you just shy or completely lost? Yeah. So yes, but here I'm taking the so this is defined as the scalar product between u2 prime of un and un minus. So this is a scalar product in the Hilbert space. Okay, so the norm of this guy is going to 0. Okay, so what I can say about this product is that it's a little low of the norm of this guy here, which is I'm using here.
So there you have both L infinity norm and H2 norm, right?
Yes, but only on a un minus, which belongs to a finite dimensional space. So if you restrict yourself to a finite dimensional space of smooth functions, as in this case, then all norms are equivalent. Okay, L infinity and H2 norm.
So in this case, suppose that the operator is positive, actually it doesn't work, right? Because
That-
lambda 1 is 0 now.
That also works because you can use the opposite inequality. So this would be greater or equal than lambda 1 times norm of un squared. The important part here is that the operator is non-degenerate, so either positive definite or or negative definite on this space. Okay, it works in both cases. Okay, nice that you are asking questions. Okay, so we get uniform bound on UN. Is the answer clear?
So what is the contradiction there? If it is not uniformly bounded, then
Oh, if so, this would go to minus infinity much faster than these two. Yes, because as a function of norm of un minus, yeah, this is just quadratic, linear, and little o1.
you don't worry about the last term.
I'm sorry.
The last term over there, you have
This one.
no the term in which you have the quotient of two integrals.
Yes.
And that is bounded by.
Yeah, because you can think of this as a measure. So divide by, you can think of dv e to the 4 un dv divided by the integral of e to the 4 un. So this is a unit measure, okay, on M, and this is just the integral of un minus over this measure. So you pick, this is bounded by the L infinity norm of un minus, which in turn is bounded by the H2 norm of un minus. Okay, so quadratic, linear, less than linear. So this term dominates, and so yeah, it has to be bounded. So now the negative part doesn't bother you no more, okay? And you can use the Adams inequality. Now, if you have uniform bounds on the negative part, then the functional is coercive, okay? So I'm using the fact that 2 of un is converging to a real constant, so the norm of un cannot blow up, okay? Even the positive part is bounded, and we have a weak limit. Claim is that the weak limit solves the equation. Okay, so how do you check that this solves the equation? Okay, you check that it's a critical point of the functional 2. Okay, what does it mean that it's a critical point? That if you test it on any given function, then you find 0. Okay, so take v in h2 of m, okay, and evaluate prime of u naught on v. Okay, just linearize the equation and test on v. So what would this be? Okay, let's okay, so this would be 2 integral of u naught pg of v, okay, plus 4 integral of q times v, and then you have minus 4 qp integral of e to the 4 un times v divided by the integral of e to the 4 un. Okay. All right, but and I want to show that this is 0. Okay, but now let's look at 2 prime of un tested on v. Okay, so now I'm fixing this function, okay, which I'm scalarly multiplying, and I know that this is tending to 0. Okay, but this is 2 integral of un pg of v plus 4 integral of q of v minus 4 qp integral of e to the 4 un times v divided by e to the 4 un. Okay, now un converges weakly to 0. Okay, so this is converging to 2 integral of u0 pg of v. Okay, this is equal to 4 integral of q times v. So it's sufficient to prove maybe I don't want to raise this. So it's sufficient to prove that the integral of e to the 4 un times v converges to integral e to the 4 u naught times v. Okay. In fact, so let's write e. So I want to prove that integral of e to the 4 un minus e to the 4 u naught times v tends to 0. Okay. So write e to the 4 un, use the Taylor expansion, minus e to the 4 u naught. Okay. So this is e to the 4 times theta of x u0 plus 1 minus theta of x un minus u0. I'm just Taylor expanding e to the 4u, okay, times un minus u0, okay, with theta of x belonging to 0, 1. Okay, this is just a Lagrange theorem. Okay, but now you have the Adams inequality. Okay, the Adams inequality tells you that every exponential term is controlled by the quadratic part of the function. Okay? So this means that if you can also put a coefficient, so every exponential term along a bounded sequence is uniformly bounded if you raise it to some power p. Okay? So the point is that this quantity is uniformly bounded in every LP. Okay? So let me recall the Adams inequality. The Adams inequality tells you that the log of integral of e to the 4u is bounded by 1 over 8 pi squared times u pgu. Okay? So if you add p here, you will find just p squared here plus a constant. Okay? So all exponential functions are uniformly bounded in LP if you have a uniform h2 bounds on u, which is the case here. Okay? But then h2 also embeds in every LQ. So this is uniformly bounded in every LQ. Okay? And then also V belongs to LR for any R. Okay? So now, if you choose 1 over P plus 1 over Q plus 1 over R to be 1, okay? So then you find indeed convergence. So this concludes the proof in that case. So this was the easy case. Okay. So if you're lost here, then the next hours are going to be hard. I'll try to do what I can. Okay. So inf of the sup of f of h of y in a. This I don't want to erase, and h in g ab. So the important things here are the deformation lemma and this condition star. Okay, so that I can apply that proposition 1. Okay, so this case was when the integral of q is less than 8 pi squared. Let me now reverse these inequalities. Okay, so for simplicity now I assume that dependence operator is positive definite. Okay, but that qp is greater than 8 pi squared. Okay, by the assumptions in theorem 2, which I raised, so q is not an integer multiple of 8 pi squared. Okay, so qp. So qp will belong to some interval of the form 8k pi squared, 8k plus 1 pi squared. Okay. So to find this get condition, what have I done here? So I evaluated the functional on large spheres, okay, to get regions where the functional is very negative. And then I used the improved Adams inequality, which I erased. So if you have bounds on the W minus component, okay, then you still get coercivity. You have still the Adams inequality, okay? So the idea is to get functions for which the functional becomes very negative, okay, but also some kind of lower bounds, okay? All right, so to verify this gap condition, I have to somehow find assumptions on U so that the Adams inequality still improves, okay? And there is now a more serious improvement of the Adams inequality. So proposition 2. So we saw before that some easy improvement was the vanishing of the W minus component. Okay, so this is a more serious improvement. So that one was very cheap, more serious. Okay, improvement of Adams inequality. So what is the improvement? Okay, I will explain in words what this means. So let L be some integer number, and let omega 1, omega L subsets of M such that the mutual distance between these sets, so distance for I different from j, of omega between omega I and omega j, is bounded by some constant delta naught positive. Okay, disjoint sets which cannot touch each other. Okay, and let also gamma naught be another positive constant. So then, for any epsilon positive, there exists some constant c which depend on epsilon, L, delta naught, and gamma naught, such that when you evaluate log of e to the 4 u minus u bar, so this is bounded by 1 over 8 pi squared L plus 1 minus epsilon, sorry, L minus epsilon integral of u pgu plus c. Okay. So I recall that the standard Adams inequality just had 8 pi squared. Okay. Well, so what is this telling you? That if the conformal volume, such that this holds for any u, such that the integral of e to the 4u in omega I divided by the integral over m of e to the 4u is bounded below by gamma naught for any I equal to 1 L. Okay, so the standard Adams inequality would be same inequality with 1 over 8 pi squared. Okay, so this is telling you that if each region omega I supports some finite amount of conformal volume, okay, I'm requiring this for any I, okay, and if these regions are distant one from each other, then you have an improvement of the constant here. Okay, so this is a more serious improvement of the inequality. So a couple of remarks that the first is that qualitatively okay, so this means that so the more the conformal volume is spread, so the more the Adams inequality improves. Okay, so if you find more and more regions which support quantitatively this volume, then you get a better constant. And the second is that for 2 dimensions and L equal to 2, so this result, so here I'm talking about the standard Moser-Tuninger inequality. The result is due to Wengshan Chen and Comminli in a paper of 1991. Okay, so what about the proof? if you scale properly, you might have some versions of that. Yeah, you can use cutoff functions, which is what I will do here. Yeah, there should be some kind of version like that. So the proof, okay, so you see that by the assumptions, these sets omega I have a positive mutual distance, okay? So this means that there exist cutoff functions Ki, so from M into R, such that Ki is equal to 1, identically equal to 1 on omega I, but Ki times Kj is equal to 0 for I different from j. Okay, so this would be the sets omega I, okay, omega 1, omega 2, omega L. There is always some distance delta naught between these sets, okay? And you can also assume that the norm of Ki in, say, C4 is bounded by some constant depending only on delta naught and the metric G. Okay, so you define these cutoff functions here. This would be Chi1, Chi2, and so on. So the idea is simple. Now you just use the standard Adams inequality on the function u multiplied by Chi I. Okay, so use Adams on Chi I times u. Okay, what do you find? That the log, we can assume that u bar is equal to 0. Okay, so u bar doesn't really bother here. So the log of the integral of e to the 4 u times Chi I is bounded by 1 over 8 pi squared times Chi I u times Pg of Chi I u plus some constant c, okay, independent of u. But I can regard this, so the principal part of the Penitz operator is the Laplacian squared, okay? So this is the integral of the Laplacian of Chi I u squared plus, say, lower order terms, okay? And this is equal to the integral of Chi I squared times Laplacian of u squared plus lower order terms. Okay, so this term depends only on, say, lower order derivatives or products of lower order derivatives with the Laplacian. Okay, so the main term is kept here. Okay. But now you can choose, you have a choice in the index I. So you can choose I so that the integral of chi, choose I bar, say, in 1L, so that chi I squared times Laplacian of u squared is the minimum over all I of chi, this is chi I bar, okay, minimum of chi I squared times Laplacian of u squared. So what do you have? That the integral of chi I bar squared Laplacian of u squared is less or equal than 1 over L times the sum for I going from 1 to L of chi I squared Laplacian of u squared, which is bounded by the integral of Laplacian of u squared. because all the chi i's have disjoint supports. Okay, so the sum of chi I squared is less or equal than 1.
When you apply this Adams inequality, usually you need a function of mean value 0. There is a normalization. Your normalization is on U bar.
Yeah, but this is some.
I of U also. There is some.
Yeah, this somehow goes into the lower order terms. It's no big problem. Okay, so we choose the index I bar in this way.
One over L here. The last term.
This is this one,
The last
one of.
Yeah, it's the last term. It still have 1 over L.
No, no. Oh, yeah. Yes. Sorry. Yes. Thank you. Correct. Yeah, that's why I get improvement. Okay, but now I'm using this condition on U. Okay, so when now we want to estimate the integral of e to the 4u on the whole m. Okay, so but the integral of e to the 4u on m is certainly bounded by 1 over gamma naught times the integral over omega I bar of e to the 4u. Okay, which is bounded by 1 over gamma naught integral of e to the 4 chi I bar u over m, because chi is identically 1 in omega I. Okay, so if you use these inequalities, then you find that the log of integral of e to the 4u, okay, using that inequality is bounded by log of 1 over gamma naught plus the log of the integral of e to the 4 chi I bar of u over m, okay, which is bounded by constant plus 1 over L integral of, say, Laplace of u squared over m plus lower order terms. And then if you are careful with the lower order terms, you find, 1 over L 8 pi squared, okay, using the standard Adams inequality. So the lower order terms give you 1 epsilon in the denominator. So that's a proof. So this actually has an interesting consequence, which is the next corollary. So look at this remark. This is telling you that the more the conformal volume is spread, the more the functional becomes coercive. Okay? In particular, if the conformal volume is spread into at least L regions, okay, then the constant improves by a factor 1 over L. Okay? So this means that if now the Euler function is going to minus infinity, then the conformal factor cannot be too spread. Okay? So the consequence of this fact is the following corollary, which you can obtain with some covering arguments. So corollary 1, okay. So suppose that k is an integer and that Qp, the total Q-curvature, is smaller than 8 k plus 1 pi squared. So then, for any epsilon and r positive, okay, which will be taken smaller, there exists some constant L, which depends on epsilon r and k only, such that every u in H2 with small energy, small enough energy, so with 2 of u less or equal than L, then minus L, there exist points P1u, pku in M. This can depend on u, okay, such that the integral over the union of the balls Br Piu times e to the 4u, this is greater or equal than 1 minus epsilon times the whole conformal volume of u. Okay, so let's look at this proposition with L equal to 2 for simplicity. Okay, so suppose that the conformal volume is spread into 2 distinct sets. Okay, then the constant in the Adams inequality improves by a factor 1/2. Okay, so this means that as long as the conformal volume is spread into 2 different regions, okay, then the functional remains coercive when the total Q-curvature is less than 16 pi squared. Okay, so if QP is less than 16 pi squared, and if the functional is going to minus infinity, it means that the conformal volume cannot be spread into 2 distinct regions. Okay, it has to be concentrated all around 1 point. And the same reasoning applies to k greater than 1. Okay, so what is the consequence? For k equal to 1, if the energy is small, okay, sufficiently negative, okay, then all the conformal volume is concentrated in a small ball of radius r. Okay, so you fix r and you fix epsilon. Okay, if the energy is sufficiently negative, then there is one ball which contains almost all the conformal volume. Okay, and the same generalizes to larger values of k. Okay, so in general, if QP is less than 8k plus 1 times the total Q-curvature of the sphere, and if the energy is negative, okay, then there are k balls in the manifold which contain almost all the conformal volume.
But the reason you wanted it to be strictly less than you didn't reach this AK plus 1 pi squared.
It's because I have the epsilon there, right?
But that is only a lower order term, is that right?
Yeah, but the lower order term usually you treat with interpolation inequalities.
That's only the first derivative of u term.
It's well, there are also third derivatives and second order derivatives because it's a Laplace of u squared.
That's because you have a cutoff.
Yeah, yeah. So the cutoff is giving you the epsilon, right? So you need a strict inequality. Yeah.
That's the only difficulty here. You do not reach AK pi squared.
There is a okay. Some definitely one condition is, I mean, one point is here, and then the other thing is about compactness. I will talk about that.
The Palais-Snell sequence also depends on this.
No. This is totally unrelated. In fact, here I'm just looking at the energy of functions, and there is no equation so far. Okay. So yeah, that proposition is telling you that if the conformal volume spreads, then the energy goes up. Okay. So if the energy stays negative, then the conformal volume has to concentrate. So I just draw a picture and then stop. Okay. So suppose you normalize the conformal volume so that the integral of e to the 4u is equal to 1. Okay, what does it mean? So if you think of drawing a picture of e to the 4u, there will be some points p1u, pku, around which you find all the conformal volume. Okay, So somehow e to the 4u will look like a sum of weighted Dirac deltas. Okay, so all the conformal volume is concentrated near k points of the manifold. Okay, so maybe we can take a break. Okay, so maybe we can resume. Okay, so what I showed here is that if you fix k and if you give an upper bound on the Q curvature by means of 8k plus 1 pi squared, then if you have low energy, the conformal volume concentrates in at most k points of the manifold. Okay, so there you can fix epsilon and r arbitrarily. Okay, and then you find an L for which that estimate holds for all u with energy lower than L. So the number L is independent of u, but the points P1, Pk can depend on u. Okay. So as I said, if you normalize the conformal volume so that the total 1 is 1, okay, then in fact the function e to the 4u looks roughly like a sum of Dirac deltas. Okay, so this is kind of suggestive for introducing this set of unit measures. Okay, so I denote by mk the formal sums of Dirac deltas. So sum for I going from 1 to k of ti delta xi. Okay, so where xi are points in M, ti are numbers between 0 and 1, and such that the sum of the ti's from 1 to k is equal to 1. Okay, so I impose this normalization on the ti's because I'm thinking of having a unit total volume. Okay, so this set in fact is known in the mathematical literature as the set of formal barycenters of M of order k. So some properties of this set so the first is that mk is a compact topological space, and the topology which is naturally induced on this space is the weak topology of distributions. So you let these unit measures act on smooth functions, and then from there you get the topology. Okay. So what does it mean? That suppose that you have two such measures which look like this. So suppose that you have 2 points which are getting very close. Okay. So this from the topological point of view is not very far from a distribution where here the weight is the sum of the two weights. Okay, so this is somehow the properties of some neighboring measures. So if I'll continue here, if you take k equal to 1, okay, so this would be just a set of Dirac deltas on M. So there is no constraint on the Ti, there is only T1 which is equal to 1, okay? And then the point x can run over all the manifold. So M1 is homomorphic to the original manifold M, okay? But in general, Mk is not a smooth manifold, is a so-called stratified set. So this is a union of open manifolds of different dimensions. Okay, so the maximal dimension is when all the points xi are distinct, okay, and when all the numbers ti are different from 0 or 1, okay. So each xi has 4 degrees of freedom, okay, each ti has 1. So the total number of degree of freedoms is degrees of freedom is 5k minus 1, and the minus 1 comes from the constraint you have on the ti's, okay. So this will be the maximal dimension, but of course you might have distributions where the points xi coincide, or when sum of the ti is equal to 0, okay. So ti can be either 0 or 1. So usually I think of this as a sort of the surface of a cube, okay. So on the surface of a cube you have sides, okay, so faces which are of dimension 2, then you have sides which are of dimension 1, and then you have vertices which are of dimension 0. Okay, this is not a smooth manifold, it's an example of a stratified set. Okay, it can be maybe not so bad, but of course from the I mean it's not smooth. And well, one important topological property is that Mk is in fact non-contractible. So you can check it directly for k equal to 1. And it's possible to prove it studying the homology of this set. In fact, the maximal homology, so the top dimension, 5k minus 1 of nk, this is different from 0. So this you can prove using some argument in algebraic topology. So somehow this corollary is suggestive in describing the low sublevels of the functional in terms of the set of formal barycenters of the manifold. Okay. Okay. So we see that if the energy is low, then conformal volume looks like a formal barycenter, more or less. And in fact, it's possible to prove this proposition. So proposition 3. Okay, so suppose that k is a given integer, okay, and that qp is less than 8k plus 1 pi squared. Okay, so we are in those assumptions. So not only you have that condition, so each element in the sublevel looks like a barycenter, but indeed it's possible to map continuously the sublevel into the set of formal barycenters. So then for L positive and large, so there exists a continuous and non-trivial continuous non-trivial map from the sublevel 2 less or equal than minus L into mk. So non-trivial means continuous map, let me call it psi, okay. Non-trivial means that psi, in fact, carries some homology. So H star of psi is different from 0. Okay. And another point is that psi is somehow natural. So this means the following, that if, let me write distance, okay, between e to the 4u and sigma, usually denoted by sigma, the formal barycenters. Okay, so if sigma is an element in nk, and if e to the 4u is, I mean, looks like sigma, okay, is small, here you can take the distance in, for example, C1 m star, okay, so the dual of the Lipschitz maps, okay, then so psi of u is not far from sigma, okay, so the distance of psi of u and sigma is small. Okay, so this means that when I project, I really map into some barycenters which resembles that graph, more or less. Okay, so this is somehow easy to say, but as I said, this set is not really smooth. Okay, so it's easy to project when you are close to smooth parts of this stratified set. But when you approach the corner, then you have to be, I mean, these singularities or corners, then you have to be much more careful. Okay, so it's hard technical work to find this global projection.
So this has something to do with this H, this MK is not contractible?
I haven't used it yet.
You haven't used it?
No, not yet. But I will say more about this natural property of this map psi.
So this is non-trivial, but has nothing to do with this space is contractible.
Somehow, because it carries some homology. So this means that the image of, I mean, some, say, singular chain is mapped to a non-trivial singular chain. So if the target set is contractible, then every map would be trivial, because that would contract to a point. It's not the case here. So since the H star is non-zero, then it means that the set is non-contractible. So non-trivial means that, but I will show you why this map is natural. So, of course, I mean, this is a very rough description of the sublevels. Okay, usually you might be familiar with blow-up analysis. People can tell you exactly how solutions look like when they blow up or so. They have this profile, and they are bounded away by a constant from the standard bubbles or so. But notice that here, there is no equation at all. Okay, so if you are trying to describe just the energy sublevels, the description should be somehow rough. Okay, and the point I want to make is that this description is somehow optimal. Okay, so here I'm saying, okay, look at sublevels, and so their shape is more or less that of formal barycenters. But the point is, that I can also embed the formal barycenters of the manifold into arbitrarily no sublevels of the energy functional. Okay, somehow I have an inverse map from the barycenters into the sublevels. So what is this map? It's this one, so proposition 4, and I will show you why that map is natural. So let k be some integer, okay, and qp belonging to some interval of the form 8k pi squared, 8k plus 1 pi squared. Okay, so start with some sigma in mk, so some barycenter. Okay, sigma will be the sum of ti delta xi for I running from 1 to k. Okay, so for lambda positive, consider this test function phi, which depends on two quantities, the number lambda and the barycenter sigma. So function of y defined in this way. So phi lambda sigma of y is defined as 1/4 times the log of sum for I running from 1 to k of ti lambda over 1 plus lambda squared distance of y xi squared to the 4. Okay, it's a horrible function, okay, but when k is equal to 1 and sigma is a Dirac delta, this is just the standard bubble centered at a point x. Okay, so why am I choosing this function? Because we have some very nice properties. So what's a nice property of the standard bubble? Okay, is that the energy is somehow the optimal one. Okay, so it's the profile which gives you the lowest possible energy when you have blow up. And one property is that when you take the conformal volume associated to the standard bubble, this converges weakly to the Dirac measure at the point x, where you are centering. Okay, so first property here is that if you consider the conformal volume associated to this function e to the phi lambda sigma, this converges weakly in the sense of measures to sigma when lambda goes to infinity. Okay, well, this is actually very easy to see, because if you believe it for the bubble, then this is obvious. What is less obvious is that the energy is still optimal. Okay, so when you send lambda to infinity, the energy goes to minus infinity. So energy evaluated on phi lambda sigma tends to minus infinity when lambda goes to infinity. And the painful part here, but the nice part, is that this holds uniformly for sigma in mk. Okay, so when k is equal to 1, of course the energy goes to minus infinity for all bubbles. Okay, but here you have to check it for all the possible combinations of the numbers ti and xi. Okay, both in case when all the points are distinct, but also when they merge. Okay, this is some painful work, but the nice thing is that you embed a copy of the barycenters into arbitrarily low sublevels. Okay, but now if we are into low sublevels, we have this map psi. Okay, so we can project back from the sublevels onto the barycenters. Okay, and I claim that these two maps are natural. So third property is that if you consider this map T lambda going from mk barycenters into barycenters, okay, which is defined as the composition of the two maps. So sigma is sent into psi of phi lambda sigma. Okay, I start from a barycenter, then I give you this test function for which the energy is very low, and then if the energy is low, I can project back onto the barycenters. Okay, and I said when some function e to the 4u looks like a barycenter, then the projection is somehow close. Okay, so guess what? When lambda goes to infinity, this converges to the identity map on the barycenters. Okay, so T lambda converges to the identity over mk when lambda goes to infinity. Okay, so I said that this map is somehow natural. Okay, so it cannot be contractible, because if I compose the two, that I get the identity or something homotopic to the identity on a non-contractible set. Okay, so this is telling you also that if you just look at the homology of sublevels, this is somehow the best you can hope. Okay, it's an optimal description in terms of homology of the low sublevels of this function. Okay, and in a sense, when you have an optimal description of sublevels of a functional, then you can run min-max schemes. Okay, so I told you that last time you cannot choose randomly A and B. Okay, so the choice of A and B has to be good and suited to that problem. Okay, so this is somehow the perfect dress for the Q-curvature equation. Okay, so I'm going to show you that the min-max scheme works if you choose as a set B exactly the set of formal barycenters of the manifold. Okay, so for the previous case, so z squared minus x squared minus y squared, the natural choice was the circle. Okay, exactly because the homology of the sublevels. Okay, let's look at this function. So f of x, y, z equal to z squared minus x squared minus y squared. Okay, so this was the zero cone. Okay, and let's look at the sublevel f less than minus L. Okay, so this would be the exterior of a hyperboloid in R3. Okay, so the homology is the same as the homology of S1, and that's why you choose S1 in that scheme. Okay, in this case, I describe the homology of low sublevels in terms of the homology of formal barycenters. So the natural choice would be to choose B equal to mk. Of course, it looks completely crazy. Okay, such a simple equation, why do you have to mess up with that set? Okay, which is very complicated, non-smooth or so. But if you look at this proposition, then you see that it's somehow very natural. I hope I convinced you. And okay, now I'm going to prove that, in fact, this choice works with this set. Okay, so mk is here. Do you remember what mk is? Can I erase it? I have more arguments later to show you that this is somehow a natural choice, even if it looks crazy. I don't know if I have time to explain them, but yeah, there are more. Okay, so choices of AB for the min-max scheme okay, so first of all, choose step one. So choose L so large that proposition 3 applies. Okay, so for energy sufficiently low, then you can find this natural map onto the barycenters. Okay. Step 2. And now we choose lambda so large that now proposition 4 holds. Okay. So such that when you take the soup of the Euler functional of phi lambda sigma, okay, so the soup now for sigma in mk, this is less or equal than minus 2L. Okay, so when I send lambda to infinity, then the soup of the image of the barycenters goes to minus infinity. I choose it smaller than minus 2L. Okay, so this soup here stands for this soup here. Because now I choose B. I write it here. So B is just the set of formal barycenters. Okay, what is the embedding of B into the low sublevels? So HB, okay, continuous map into the Hilbert space. So HB of sigma is phi lambda sigma for this choice of lambda. Okay, so I want to prove this gap condition. Okay, so I want to push this value down. Okay, so this is what I'm doing here. All right. So what's the choice of A? So recall that for the other case, I started from a sphere. So I was using Sn-1 as B, and as A, the n-dimensional ball. Okay, so I want to construct it with a process which might recover that choice as well. And now I come out with something which looks again crazy, but it's in fact very natural. So what is the choice of A? Okay, so I take the product mk cross 0, 1. Okay, I told you mk is not smooth. It looks like, say, a square or say the surface of a cube. Okay, and I take the product with 0, 1. Something like this. And then I define an equivalence relation. Okay, so I want the top part to be identified with a single point. So I introduce some equivalence relation, tilde. Okay, so mk cross the single point 1 is identified to a point. So what does it mean? You shrink the top of this product. Okay, so this becomes like a pyramid. Okay, this is what you get. This is a standard construction in topology, so this is called the topological cone over mk. Looks stupid, but in fact it's a way to recover the ball from the sphere. Okay, so the claim is that in fact star holds so star holds for these choices of A, B, HB. Okay, why? Proof with and say delta equal to L over 2. So proof, okay, suppose star is false, okay, then what does it mean? Then we can take an extension of this map HB, okay, so a continuous map from the topological cone into the Hilbert space, such that the sup here is less or equal than this sup plus L over 2. But this sup, by my choice of lambda, is less or equal than minus 2L. Okay, so then there exists H in GAB such that, so the sup for y in A of 2 of H of y is less or equal than minus 3 over 2L. Okay, that's a contradiction. But remember that I chose L so that this proposition 3 applies. I erased it, sorry. Okay. So what does it mean? That from the sublevel 2 less or equal than minus L, so we are in there, you have a continuous projection onto the buried centers. Okay. So this means that so there exists so composing with phi with psi, sorry. Okay. So the image will be in this sublevel. Then there is this image from the sublevel onto the buried centers. Okay. So there exists a map, let me call it theta, from the topological cone into B, which is mk, such that theta restricted to the bottom of the cone here, okay, which would be B, okay, the image of B. So theta of dot 0 is homotopic to because it will exactly coincide with this composition. Okay, so this is homotopic to the identity on mk. All right, but now what can you do? So you look at the image of this map, okay? So this is homotopic to the identity. So you can deform the identity to that map, okay? And then if you just squeeze the value of t, you can deform the identity to a constant, okay? So you would obtain a deformation of the identity map on nk to a constant map. And this is impossible because mk is non-contractible, okay? So impossible. This would be a contradiction. Should I repeat?
So
yes.
Up to this point, you didn't use the fact that QP is in that interval?
No. So in fact, this proposition requires two conditions. One is star, which I just verified, and the other is the Palais-Mail condition or the deformation lemma. And for that, I need that condition.
This is completely general.
This is completely general. Yes, it's purely topological, say. Is this part clear? I know that you are not shy, so you can ask questions if you don't understand. So the base map, once I do the composition, is homotopic to the identity, okay? And then just deform, okay, you could deform to a constant. So this is where I use somehow the optimal description of the homology of the sublevels, okay? So usually you can run these schemes when you have an accurate description of the sublevels, and when you notice a change in the topology. Okay, so the topological part is somehow fine, okay, if you believe me. And let's check the deformation lemma now. Okay, so I recall the remark saying that you can replace the Paley-Smale condition with the deformation lemma. In fact, it is not known whether the Paley-Smale condition holds for this problem. So that's an open problem. But in fact, the deformation lemma is known. So the next issue will be compactness. And deformation lemma. Okay, so this is where I will do blob analysis. I will use the equation, and so you are all familiar with this part. Okay, there's a theorem. So it's independent work by Drouet, Robert, and myself in 2006. Okay, so suppose PG is non-degenerate and QP different from 8k pi squared with k in n, then solutions of dependence equation are bounded and compact by the Ascoli theorem in every Cm alpha. Okay, why? Well, I will just have, I will just use a few minutes to explain it. So proof it's sufficient to prove that solutions are uniformly bounded from above, because then you can start with the elliptic regularity machinery. Okay, so by contradiction, assume that there exist UI solutions with the sup of UI, which is attained at some point xi, tends to infinity. So now you know how it works. So use local geodesic coordinates around xi, okay, and you rescale the function so that the supremum is bounded. Of course, when you dilate such an equation, you keep just the main order terms, okay? So after dilation, this has to converge, the equation has to converge to the bi-Laplace equation in R4. So all the lower order terms in the dependence operator are gone, and you keep the exponential term. So in this coordinate, set vi of x to be ui of x over mu I. Yes? Here. Can you read here? Okay, I just wrote set. Set. Okay, so scaling this way. Mu I is e to the ui of xi. Now the sup of vi will be 0. Sup of vi is equal to 0. And vi converges in C4 alpha log over 4 to V naught, where V naught, say V bar, sorry, where V bar satisfies Laplacian squared of V bar equal to 2 Q bar e to the 4 V bar. Okay, now you have an entire solution in R4 of this equation. There is a classification result by Chang-Shu Lin from 1998. So this result tells you that either V bar is a standard bubble. So this is a log of lambda. Actually, lambda should be determined by this condition. Say lambda bar plus lambda bar squared mod x squared plus 1/4 log of 48 Q bar. There's a horrible constant depending on this Q bar here. Okay, so either you have this standard classification, or V bar is a quadratic at infinity. But then if it's quadratic at infinity, this means that the Laplacian of V bar in this condition is equal to some constant A, which is negative, because it's actually quadratic negative. Okay, and this you can rule out. Using the Green's representation formula, so using the fact that the dependence operator is non-degenerate, and you have a Green's representation formula. So Green's representation formula. So this follows from the fact that the kernel of PG is just a constant functions. So rules out the second possibility. Oh, my pens are probably gone. Okay, so the limit is just a standard bubble. Okay, so what's a nice consequence? So now we don't care about topology. Yeah, this is what I want to say next. Not immediately, so you need to work a little more. So the fact that V bar is a standard bubble, so V bar bubble, implies that the integral of 2 Q bar, integral e to the 4 V bar in R4 is equal to 8 pi squared. So this reflects that the limit profile is the sphere. So this integral would be the total Q-curvature of the standard sphere, because V bar is the conformal factor of the stereographic projection. Okay, so since integral of Q-curvature is a conformal invariant, then you pick up the total Q-curvature of the sphere. So that tells you locally, because we scaled, okay, so this means that there exists a sequence of radii Ri tending to 0 in general, so that when you integrate Q bar e to the 4 ui over b Ri of xi, so before scaling, this converges to 8 pi squared. Okay, so more work. Okay, implies that indeed, so you can localize this estimate that the integral over the whole manifold of e to the 4 ui times Q bar, in fact, must be an integer multiple, so tends to 8k pi squared.
Where does k comes from?
For some k. So that would be the number of blow-up points. Yes. So this means that if QP, so the consequence is that QP different from 8k pi squared implies that solutions implies compactness. This is compactness of solutions, okay, not quite the deformation lemma. Oh, I have to recall that in 2D there were previous results by Berzis, Merle, Yan Li, and Shafir. So this is a fourth order equation, so a little more difficult, not so more difficult, okay. And well, let's erase this nonsense. Once you have this, in fact, you can also prove the deformation lemma. Not in 2 lines, but in 2 pages. Okay. So there is this proposition 5. Okay. So PG, if PG is invertible, QP different from 8k pi squared, then the deformation lemma holds. In fact, okay, this actually holds for an analogous 2-dimensional problem, not necessarily related to the Q-curvature equation, to the Gauss curvature equation. So, in fact, this follows from ideas or previous works by Michael Struve and Marcello Lucia. So, if you modify some previous results, especially the one by Marcello Lucia, which is inspired by some work of Struve, then indeed you get the deformation lemma. And okay, then the proof of theorem 2. So this follows from proposition 1 star and deformation lemma. Theorem 2, no, is my theorem with Winjaya, so existence for the Q-curvature equation. And yeah, I will stop writing. I will tell you in 1 minute some advertisement, okay? So first of all, the results have been extended in higher dimension by Njaya, so a former student of mine. So he studied the critical equation in a higher dimension and also for manifolds with boundary. Okay, you have to choose the right boundary condition. It's related to the so-called Q-curvature, T-curvature introduced by Chang and Qing. But in fact, there is also a physical equation in 2D, which is an extension of the Gauss curvature equation. Okay, so the physical equation, I said I wouldn't write anything, but I lied. Okay, so delta U plus rho equal to h of x times rho times e to the 2u. Okay, so this is an extension of the Gauss curvature equation, and it has similar variational features. Okay, so this holds on 2-dimensional surfaces with a metric G. And in fact, with this approach, we could get new results even for this equation. So there were some works by Chen and Lin in which they got existence computing the Leray-Schauder degree of this equation via hard blow-up analysis. Okay, so at the critical values of rho, here they would be multiples of 4 pi, you have possibly blow-up of solutions. Okay, so they computed the degree. And in fact, this method gives, first of all, existence even when the degree is 0. So for all surfaces and for all non-critical rows, you can get multiplicity results. So my student Francesca De Marchis is working on that. And also you can get a very clean proof of the degree counting formula by Chen and Lin. And you can also get the degree for the Penitz equation. I don't write it because it's a big formula. So, but I stop here, and thank you for the attention.